Last time we looked at how we derived the conservation of mechanical energy equation. Now let's take a look at how to use it. It says a roller coaster car is released from rest at point A. Now that rest tells me something. If it's at rest, that tells me its kinetic energy at the beginning, its initial kinetic energy is 0 because its initial velocity is 0. It travels along the track shown. Assume that the track is frictionless. That's nice. That means we don't have to worry about any reduction of energy because of friction. So, at which point will the car have the greatest speed? Okay. Now I want you to think about this. We know it's not A. A is at rest. Where's it going to have the greatest speed? That means it's got to have the greatest mechanical, or not the greatest mechanical energy, the greatest kinetic energy. Mechanical energy stays constant though. So anywhere on this roller coaster, 1/2 mv squared plus mgh equals a constant. Okay? This is never going to change. So if I want the most speed, I want this number to be the biggest. That means I want this number to be the smallest. And that's going to happen down here at F. And so my reasoning here is all the energy is kinetic. None is gravitational. If there's no gravitational energy, then it's going to have the most kinetic energy because it started with lots of gravitational potential energy. At which point will the car have the greatest potential energy? Potential energy actually is the energy that something has due to its height, and so I'm going to go ahead and I'm going to look for the highest spot, which is right here at A. It's the highest. Okay. Now, I don't want you to think that if something's moving slow, that automatically means it has potential energy. Potential energy comes from its position above the ground because of its height, because gravity can pull it down. If something's already on the ground, then it can't really fall any further. It does not have potential energy, regardless of its speed. At which point will the car have the greatest kinetic energy? Well, this is F, because if it's moving the fastest, it's got the most kinetic energy. The potential energy at B, how does it compare to the potential energy at D? Okay. Well, here's point B, here's point D. Which one has more potential energy? Well, point B is a little bit higher than point D. So their difference in potential energy is this distance here, and since B is higher, it has more potential. So the potential energy at B is greater than the potential energy at D because it is higher. Now we're supposed to compare the kinetic energy at C and E. C is here, E is here. Okay, so C has more potential energy because it's higher. E has less potential energy because it is lower, but we're supposed to be looking at kinetic energy. However, if the potential energy is less, that means the kinetic energy is more because the total energy stayed the same. So we know it's moving faster at E, has more kinetic energy at E. So the kinetic energy at C is A less than the kinetic energy at E because more of the energy is potential at C, and so that means more of it's kinetic at E. So it's just a trade-off of one point to another.